So to start with an announcement, so remember our test 1 is Friday next week, so February 28th. Of which Maris was informed, is highly informed of this.
Yeah.
So test 1 is on Friday, which means no quiz on Tuesday. So you have that. So
Yeah.
next week, the only testing you have to worry about is the actual test, which is Friday. Yeah.
What about the following Tuesday, like after the exam on Friday?
Yeah, I'll do.
Oh, okay.
Because I'll be teaching the whole time. So the test on Friday is going to cover everything up to what we get to today.
Okay.
So I'll continue teaching on Tuesday and Wednesday, and so the quiz the following Tuesday is going to be on what I teach on Tuesday and Wednesday. But as for the test on Friday, you can ignore everything I talk about on Tuesday and Wednesday. But I'm going to keep teaching. So the following Tuesday, yeah, we go back to the quiz idea. But next Friday we have our first test. It's going to cover everything up to implicit differentiation, everything that we do today. Today we're going to just pretty much do some more examples, and a slight little trick that we can do with implicit differentiation. But that will cover everything for the test. And we're about a week out, so what I will do is today, whatever day is today, I'll post a review. So I'm not going to do a review in class. I'm going to, on the class website. So I'll post a review. So that's at Jhevon.org/teaching. And then you click on the class 1203. So basically I'll post some instructions. Here's how you go about preparing for the test. Here's what you have to study. Here's a list of topics. Do this, do that. And then I'll actually put a mock test. Right, so you can see an example of what a test might look like.
Okay.
So it's going to be pretty close to that. But it's important that you go through like how I tell you to study and go through the test and the follow-up and all that. I'll post instructions on everything, like how you want to study around this test to make sure you actually do well. So I'll post a mock test and yeah, as well as instructions on how to actually do it. And the idea, of course, being that ultimately I want you to take the mock test under the conditions of the real test, which is basically what I'm going to say. So don't just open the mock test and start looking at the questions. You definitely want to start studying before, and then when you do the mock test, pretend it's an actual test, right? So time yourself, don't get help from anybody, actually try to do it all in its entirety in one sitting, and see where you are from there, and then you can follow up and know what you need to fix. So I'll post instructions on how to do the review, but today I'll post a review. So that's that. As for what we're going to be doing today, more implicit differentiation, and I'll show you a trick that we can do with implicit differentiation, and that's all you will need to know for the test. So the test covers everything up to implicit differentiation. So, like I said, no in-class review. I'm just going to continue teaching next week. Whatever I teach on Tuesday and Wednesday of next week, I'll move those guys to like a bonus section for the test. So I'll give you a bonus on the test, just like on the quizzes. So I might put those sections in the bonus, or maybe even the next section I'm about to teach in the bonus as well. But everything you need to know for the test, it's whatever up to the end of today's class. So yeah, that's just an announcement, making sure that we haven't forgotten. So February 28th is our test date.
Same day as the chem test.
What? What?
Same day as the chem test.
That's the same day?
Yeah. Sure is.
Oh, well, my test is going to be easier. You guys.
Yeah. Yeah.
Make sure you study for my test first, right? The chem, no one knows. Like, you need to pray, you need to go to temple, you need to do whatever you can do. But I think if you follow what I tell you, you'll have a good shot at this one, actually.
Yeah.
I think you'll be fine if you approach it the right way. Chem, like, who knows? You can. You're definitely not getting a mock exam for your chem test. I don't
Yeah, we
think.
are.
You have 4.
You are?
Yeah, we do.
four
We get like
exams.
practice exams, but like they're really hard, so bye.
Oh my God, I'm actually.
We'll see the actual test. Like mine,
Tears are coming.
I'm gonna
Jhevon.
make it look like the review, so you're not gonna be surprised. Like if you can do well with what I give you, you're gonna do well on the test for sure.
I
So.
don't know what's been going on.
Don't
Time.
Don't
repeat that. Don't repeat that.
So
That is so scary.
we were ending with an example last time of Van der Waals equation.
Yeah.
Chemistry.
God, this is making me upset. No,
I'm not feeling this example. Okay.
Totally
So it's P. Is anyone doing physics?
God, no.
Maybe next time for the next class I'll do a physics example to, and we wanted to find dV dt. What's the answer? Okay. And we actually, I think we started this, but the idea is if you see something like this, you don't have x's and y's, don't get yourself confused because there are no x's and y's and you're used to seeing x's and y's. The important thing is knowing that the guy in the bottom, that's your independent variable. So the p in this sense is kind of like your x, and the v is your y, right? So this is a dependent variable. So similar to x from before, where this one is similar to y from before. So you want to go through and you want to identify who's your independent variable and who's your dependent variable. Now that's important because whenever you're differentiating an independent variable, you don't really have to do anything. You just apply the calculus rules and you don't have to make any concessions for that. However, if you're differentiating the dependent variable, you have to multiply by y prime, or the prime of the dependent variable. So every time you differentiate a v, you have to multiply by v prime, or dv dp, because the v, you want to think of it as an inside function of p, right? So you're thinking of the v as a function of p, and so you don't really know what it is, you have to use the chain rule. But when you're differentiating a p, you don't have to do anything. So, other than that, nothing else really changes. You would differentiate both sides, and I think we did this stuff last time, but I'm not remember.
Yeah.
Differentiate both sides. Now, again, remember, all your derivative rules still apply, so the product rule is still a thing, quotient rule is still a thing. All the rules are intact, it's just the way you're applying them, it's slightly different. So, you're just going to go through and differentiate the whole thing. And on the left side, we realize, oh, it was really the product rule, because I have one function times another function. So we differentiated the first function, leave the second one alone, plus you're going to leave the first function, and you're going to differentiate the second function. And the derivative of that is going to be 0. So the derivative of the first one, the derivative of p, that's like me asking what's the derivative of x, it's going to be 1, right? So plus the derivative of that. Now what we did here was we thought of this as 5v to the minus 3, and we differentiated that. Now that's going to be initially the power rule, so that comes down and gives us a minus 10, because the minus 2 comes down, multiplies to minus 5, v to the minus 3. But then you have to remember, your v is the dependent variable, so you have to multiply it by v prime, right? That's going to be your dv dp. So you go through your derivatives as usual. The only difference is whenever you're differentiating a v term, multiply by v prime. If you're differentiating a p term, you don't have to do anything. So that's the derivative over there. Over here, derivative of constant was 0, derivative of v is, well, v prime. And so now, at the end of the day, what you want to do is you want to isolate this guy. So you're just going to go through, and now it's an algebra problem. What you're going to want to do is multiply out all these guys and solve for v prime. So remember how to multiply out parentheses. Just start with each term in one, multiply everybody in the other one, and add them all together. So 1 times this times this. So 1 times v is v, 1 times this is that, minus this times that. That's going to be minus 10v to the minus 2v prime. minus this times that, that's plus 0.3 v to the minus 3v prime. Multiplying this out, p times v prime. Multiply this out, I get 5v to the minus 2v prime. And I can combine these. See, this guy and that guy, these are actually like terms, right? So I have minus 10 v to the minus 2v prime, and I have plus 5 v to the minus 2v prime, right? Minus 10 apples plus 5 apples. So I can actually combine those two. So this is just minus 5 v to the minus 2v prime. Yes?
For the notation, because last class you, instead of doing v prime, you wrote out dv dp, so would you rather have us do v prime?
I don't particularly care, it's just that the last class I really wanted to emphasize who was the independent variable versus the dependent variable. In this case, I think it's fine if you just use the v prime, but just as a general case, I'm not going to test you on this in next week, but just in general for you to know, sometimes you can have even more than two variables, so you have variables all over the place. And so when you're saying a prime, it's not going to be clear, prime, who are you talking to, right? So what you would do is you write out this notation so everyone knows, okay, now I know who is the main variable and everyone else depends on that, right? But yeah, once I write v prime here, it should be clear that the p is the independent variable. But if there was a third variable like a t, then a v prime wouldn't be good to write, because then I'm not going to know, is the p the right one or is the t the right one? So if there are only two variables, it's okay to write a prime. Once it gets to more than two variables, it starts to get confusing. So last time I wrote this for emphasis. But it's okay to use the prime notation here with two variables. Yeah, so now I just want to solve for the v prime. So I just want to isolate all the guys with the v primes here. So everyone who doesn't have a v prime can move to the other side. Right? So on the right side, I'm going to add the point 0.03 and then subtract the v. So those guys go away. And on the left side, v prime is a common term, which I can factor out. And I'd be left with minus 5v squared, v to the minus 2. And 0.3v to the minus 3. And p. So then ultimately, my dv dp, or my v prime, is going to be equal to 0.03 minus v all over that would be your answer. Now, let's do a couple more examples to make sure that we have this this hammered home, and then I'll show you a little trick that implicit differentiation can allow us to figure it out. More examples. This is find y prime, which is d by dx, if we know that 4x squared plus 2xy minus 3x squared y squared plus 4 equals 7x. B, if we know that e raised to the x plus y squared plus ln of x plus y equals 3. actually give you guys some time to try these, so. So one problem for the test next week, it's going to have this kind of format. Basically, in one of these problems, I'm gonna give you like 5 problems and just say find the derivatives of all of them, right? So it's like problem 2, parts A, B, C, D, E, right? Find the derivatives of all of these. 4 of those are gonna be like the regular derivatives that we were doing like the past couple of classes. And then one of them is gonna be an implicit differentiation. So I might give you an expression like this. Say find the derivative. That's gonna be one thing that you have to do. So actually try those. Give you guys about 8 minutes to try both of those, I guess. Which is longer than you'd be expected to do on a test. Like I budget like 2 to 3 minutes per derivative problem. That's kind of what you want to aim for. Did anyone finish the first problem? That's about our cue. Alright. What do we do here? What did you draw? Do you wanna go? Okay.
Sure. So it would be 8x plus 2, open parentheses, x times y prime plus 1 times y, minus 3, open parentheses, 2xy squared plus 3x squared times 2y times y prime equals negative 1 over x.
Yeah.
So
if you open the parenthesis here,
yeah, for the x squared times.
so why is there a 3 here?
Oh, sorry, that would just be x squared.
So if you open the parentheses, you don't need it. So that's x squared times,
Times y times, or times 2y times y prime.
plus,
0,
equals.
negative 1 over x.
That's fine, that's correct so far. You didn't really need to open the parentheses though. I would probably, in this situation, I'd probably think of the 2x as one of the functions, and then the 3x squared as another one of the functions. Ultimately, I'm gonna have to expand all these parentheses anyway, but if I think of it just like taking the constant as a part of one of them, it actually saves me from having to multiply out. So instead, I probably would have jumped to differentiate. This is 8x here. Differentiate the 2x, that's just 2y plus leave the 2x, differentiate the y, that's y prime. Which when you multiply out, you get this back anyway, right? But it saves you that step of having to multiply out. Then think of the minus 3x squared as a one function, so I differentiate that, leave the y squared, then I leave the minus 3x squared, differentiate the y squared. And when I multiply out, I would get the same thing. That's of course 0, and this is 1 over x. So, but from this line, you would have gotten to here anyway. So what did you do after that?
Wouldn't that be 2y y prime?
2y, where?
Right before the equal.
Yes. Okay, but after that, now what?
Now you'd subtract the 8x and add the 6x.
Subtract the 8x, add this,
And subtract the 2y.
and subtract the 2y. So you're getting rid of everyone that doesn't have a y prime, yeah, then?
And then pull out the y prime.
Well, this now is going to be 6x squared y.
And then divide by 6.
That's fine. It's a compound fraction though. Probably if this were a textbook, they would multiply by x over x to get rid of that fraction right here, but that's fine for us. What about b? Did anyone get through b? Or were there any questions on this? We understand what happened? So if I have like a constant in front of something, I would just take that constant as a part of the function. It'll save you a step. Try it, yeah.
You find the derivative first. That would be e to the x plus y squared times 2y y prime plus 1 plus y prime over x plus y. You close
Oh,
you
you close this here?
Yeah.
Yeah, no, something's off. What's the problem here? What is the rule? What rule are you using?
So e times u prime.
Well, the derivative of e to the u is u prime e to the u, right? That's the rule. What's your u in this case?
X plus,
It's this whole thing,
yeah,
right? That's like the u. So what's the derivative of that?
1 plus.
Right, so you're missing that 1 plus. So the derivative of the x is 1 plus the derivative of the y squared, well that's 2y y prime. So that's the derivative of the first part, just following the rule. Now, plus,
1 plus y prime.
so you didn't forget a 1 plus in this case, so that was just like a hiccup or something.
X plus y equals 0.
0.
And then I multiply everything, well, both sides by x plus y. And then move the 1 to the other side. Well, negative 1, right?
And we would have x plus y e to the x plus y squared times 1 plus 2y prime.
So then you would factor out the y prime.
Y prime isn't a common term. There's no y prime in this part.
Oh, right, I forgot the 1, sorry. Yeah, that's my.
Oh, you forgot, yeah, forgetting it here changes everything here. So what we need to do, we actually need to expand the parentheses here. We need to actually multiply that out. So I would just take this whole thing here, multiply by 1, multiply by that. And so we have to multiply that out, so this is x plus y, e to the x plus y squared, plus 2y prime x plus y, e to the x plus y squared, plus the y prime equals minus 1. So now, the y prime terms are here and here, which means I need to move this to the other side and factor out my common y prime. So what's left over here is the 2y x plus y e to the x plus y squared plus 1. And so that means my y prime equals minus 1 minus x plus y e to the x plus y squared all over 1 plus 2y x plus y e to the x plus y squared. That's that. So here's an interesting trick. We know how to find the derivative of x to the n, right? So that's just the power rule. What you'll notice here is that your x is your independent variable, and your n is just a constant, right? So if I have x to a constant, I know how to differentiate it, right? Just n x to the n minus 1. Bring the power down, subtract 1 from the power. But what about something like this? What if I wanted to find a constant raised to the x and find his derivative? Or, even worse, what if my base is a variable and the power is a variable at the same time? Does the power rule actually apply? Can I just move the power down and subtract 1? It turns out the answer is no. That's not going to be true. How do you be able to find the derivative of, if your base is the constant and the power is the variable, or if both the base and the power has variables in it? So here's what we can do. Set y equals a to the x, and just know that we want y prime, right? Now, what you can do is, because the variable in the power is kind of making things complicated, you can use logs to get rid of exponentials. So I would just log both sides. Now, that allows me to bring this x down like that. And now what I can do is, now I can just perform implicit differentiation. The derivative of ln y is y prime over y. The derivative of x times ln a. A is just a constant, right? So a greater than 0, a constant. So if I have x times a constant, what's the derivative? Well, it's just a constant. And so now what I can do, since I want y prime, I can solve for y prime. Y prime is just going to be y times ln of a. But what is my y? My y was e to the x. So that is another rule. So this leads to, we have this new definition here. The derivative of a to the x is a to the x ln a. Now, one thing you can notice that is, if your a is equal to e, it just becomes e to the x ln of e, and ln of e is 1. So this rule would include e to the x. right? But it actually works more generally than e to the x. So I could do some other number, like 2 to the x. So for example, if I ask you to differentiate 2 raised to the x power, right? It's very different from saying x raised to the second power. The derivative of this one is 2 to the x ln 2. And with the chain rule, I can generalize this rule a little bit. Suppose I have a constant base and the power is not just x, it's some function of x. Well, that just means you differentiate the outer function and multiply by the derivative of the inner function. So that's the chain rule version of the rule. So an example where that would apply is, let's say I had the derivative of 3 to the x to the 5th plus 1. How do you differentiate that? Well, that's just like an a to the u, where this is your u. And so it's going to be u prime, which is 5x to the 4th, times a to the u, which is the original function, times ln of the base. And that's your derivative. Now, the above technique, notice what I did was I had something that I wanted to figure out, but because it had an issue with the power or something like that, what I can do is I can take the log of both sides, figure out the derivative with implicit differentiation, and then I can solve for the y prime. And that's actually a nice technique that we can pretty much apply in almost every case, but it's particularly useful in certain cases. The above technique is called logarithmic differentiation. It's when you apply logarithms to both sides of an equation to make taking derivatives easier, and then you can just solve for it. And ultimately we got a rule out of that. So this is just another rule that you know now. So this basically means, so if given y equals f of x, to find y prime, we can log both sides. And simplify the right side. So this is particularly useful when the right side is kind of complicated. We don't have a rule for it. And 2, differentiate implicitly. With respect to x, and 3, solve for y prime. So that technique is called log differentiation. Because we know the power of logarithms to simplify things. They turn powers into products, they turn products into sums, they turn divisions into subtractions. So a log can actually make things a lot simpler. And so we have a technique called log differentiation, where we introduce a log even though a log wasn't there in the beginning. What about, say, x to the x? Now that one's different. So again, I want you to appreciate the power rule does not apply, because for the power rule to apply, the power needs to be a constant. Also, this rule does not apply, because for that rule to apply, the base needs to be a constant. It's very important that you know the rules, you know them exactly, and so you know when you're in a situation where one can be applied. So we don't have a rule that covers this case yet, where both the base and the power of the constant is a variable. But what we could do is log differentiation. So if you have something that's really weird, but it's like a power and a product, and it's really complicated in terms of calculations, you can apply log differentiation. So I would just set y equals x to the x. I would log both sides. This will allow me to bring the power down. And now I differentiate, right? Once I simplify the right side. The derivative of the left side, y prime over y. The derivative of the right side, how do I differentiate x times ln x? over x times 1. Doing fine? Yeah, it looks fun. No, don't forget your training grasshoppers. X times
Oh,
ln x. Yeah.
use the product.
You need the product rule. You can't just differentiate each piece and stick it together. Don't forget your training. You have a multiplication of functions. You need a product rule. That's one function, that's another function. So I'm going to differentiate one, leave the other, plus leave the first one, differentiate the second one. So that's actually ln of x plus 1. And so now my y prime is going to be equal to y times ln of x plus 1. And my y was x to the x. So this means that the derivative of that is x to the x times ln of x plus 1. So that's your derivative. And that's log differentiation. So I would know that this, the answer to this, the derivative is actually x to the x times ln of x plus 1. You can figure that out with log differentiation. So I'll give you some examples to ponder. Examples. Find y prime equals dy dx. So suppose I ask you, what is the derivative this one, the derivative that, right? Which is a very nasty chain rule problem if you were going to do it directly. But you could actually use log differentiation and make that a lot easier. So try those for next time. And in terms of what you'll need for next week's test, we have everything. I'll post a review later.
So all the tricks that we just learned, those, everything, that's all gonna be on the test, right? And then everything on.
Yeah, you might have to use log differentiation for it.